Hypothesis testing is essentially the first step in statistical analysis. It translates your research question into a testable claim and ensures clarity and precision in the analysis. Suppose we have this research question. Is there a difference in diastolic blood pressure between males and females in the Framingham Heart Study? We translate that research question into statistical hypothesis. And we have two competing hypotheses here, the null hypothesis and alternative hypothesis. The null hypothesis states that there is no difference in diastolic blood pressure between males and females, and the alternative hypothesis would be difference does exist in diastolic blood pressure between males and females. The null hypothesis is commonly denoted by the symbol H0, and alternative hypothesis is denoted by H1. In statistical hypothesis testing, an analogy is often drawn to the legal process. The null hypothesis represents not guilty, assumed true unless evidence suggests otherwise. The alternative hypothesis is like guilty, only accepted if data provides strong evidence. Just as courts require proof beyond reasonable doubt, statistics require sufficient evidence before rejecting the null hypothesis. Here are the steps in hypothesis testing. In the first step, you state the hypothesis. That is, you convert your research question into two competing statements, what we call the null hypothesis and alternative hypothesis, as we just did in the previous slide. And then you choose the significance level alpha, which is typically 0.05. In fact, in health research, it is invariably 0.05. You collect your data and calculate the test statistics. Then you find the p-value. If the p-value is less than 0.05, you reject the null hypothesis and accept the alternative hypothesis that there is a statistically significant difference. But if the p-value is bigger than your significance level alpha, that is 0.05, you fail to reject the null. So you need to be careful in your wording. We use these exact words, that is, we fail to reject the null if our p-value is above 0.05. In our question for diastolic blood pressure between males and females, our null hypothesis would be that the mean diastolic blood pressure of males is equal to the mean diastolic blood pressure of females, and our alternative hypothesis is that mean diastolic blood pressure of males is not equal to the mean diastolic blood pressure of females. In step 2, we choose the significance level, which, as we just discussed, is typically 0.05, and that defines the acceptable risk of type 1 error. And then you go ahead and collect data, including diastolic blood pressure for males and females. You perform the appropriate test, maybe 2-sample t-test or ANOVA or whatever you would like appropriate for your analysis. You calculate your mean, standard errors, and t-statistics. And then you find a p-value. As in fact, when you will conduct your statistical test, p-value will anyway be calculated as a part of those results. You look at your p-value. If it is, say, suppose it is less than 0.05, it is 0.03, then you go ahead and reject the null hypothesis. You make these decisions, if p-value is less than 0.05, you reject the null, that there is a statistically significant difference between the diastolic blood pressure of males and females. And if p-value is above 0.05, you state that we fail to reject the null hypothesis, stating that there is no statistically significant difference in diastolic blood pressure between males and females. Since our p-value was less than 0.05, we can conclude that there is a statistically significant difference in diastolic blood pressure between males and females.